All right, so we're going to calculate this chi-square statistic, right? And I'll say, right, it is strange that we are calculating expected minus observed for both before 1980 and 1993. But the reason that we're doing this is we're trying to see if our counts for before 1980 and our counts for before 1990 are homogeneous. Okay, so that's why we're able to group that like that. So that's what our chi-squared statistic is going to look like. We are going to go ahead and use our calculator to calculate it. So I'm going to go to my calculator. On my calculator page, I have to create a matrix. I'm going to give the matrix a name, birthday. I have to hit this key right here. So I hit Control, and then this weird colon equals sign should come up. Then I hit this same key again. That key allows me to create a matrix. So this right here is our matrix. So I click that, and it asks me for my matrix, how many columns and how many rows. The number of rows we're going to have is 7. Our number of columns is going to be 2. We hit enter, and now we've got to put the data in there. And the best way to do that is hit a number, hit tab, hit the number, hit tab. It'll have you cycle through it. So I'll hit 12, tab, 9, tab, 12, tab, 11, tab, 14, tab. Once I finished entering all that, I hit the enter key, and it stored that matrix under the name birthday. And what's awesome is that, I did spell birthday right this time. That's amazing. I know how to spell. The cool thing about this is that it is taking my expected. It's gonna do all these calculations for me. Right, all it needs is my my observed counts. That's it. It will find my expected counts. It will calculate probability and all of these things. So let's go ahead and do that. Let's go ahead and now perform a chi-square two-way test. So I'm going to hit Menu, Statistics. I'll go to Stat Tests and hit chi-square two-way test. And now when it asks me for the observed matrix, I have, let's use the one that's spelled right, birthday. I'll hit OK, and it has done it for me. All right, so it's way fast. It's just that you have to remember how to do it. But now it's recorded for posterity, so you're good. There's our chi-square value. That's what we really wanted. So let's go with approximately 6.549 for that. Oops, wrong one. You didn't or you did? I said 549, right?
6.549, yeah.
Hey, we did it. It was a little awkward and at times embarrassing, but we did it. Here we go. We calculated it. Let's go. As a matter of fact, we have a lot more done. All right, so we started this significant test, right? And our null hypothesis that there is no difference in the distributions of birthdays for people born before 1980. And our alternative hypothesis for this is going to be that there is a difference in the distributions of birthdays for people born before 1980 and people born after 1993, right? We wrote that big old long sentence a long time ago. All right. Let's go ahead and finish the problem. Let's actually bring this thing to a conclusion. So, what are the conditions for this test? Our conditions are going to be, was it random? It did say it came from a simple random sample, right? So we could say the data comes from an SRS, all right? And then we need to check that our sample's large enough, right? It was what? So we're talking about number of births, right? Was it 100 or 150? It was 148. Right? Did I get? Wait, that was our 150. Oh my gosh, where did I get 148 from? Right. So n was 150. And that is going to need to be cool. So is it safe to say that didn't we check this condition? Okay, perhaps not. So 1,500. Do we think the total number of births is going to be greater than 1,500? Yeah. So we can assume. They're all births, aren't they? They're just births. We can assume the total number of births is greater than 1,500. Okay, so that's checked. Are each of our expected counts greater than 5? So I'm not going to write them all down because we have them here. So if we had this table, in order to check our condition, we could say all of these are greater than 5, right? And that's what I would do. If I had them all on the same page, I would point to that and say all expected counts are greater than 5. Because you're not allowed to just say all expected counts are greater than 5 somewhere on your paper. You must actually have all expected counts in order to prove that they're greater than 5. It's not enough to say that they are. You have to actually point towards the actual expected counts. Okay? But I said that, and now I'm just going to write all expected counts are greater than 5. And just to cover myself, I'm going to put C table. Okay? I just feel bad about writing something down that I told you not to write down and then calling it good, right? It's all in the table. Okay, boom, A is done. Let's use table C to find our p-value. We've used our calculator, right? So our p-value, we know. Let's go. Calculator is equal to 0.365. Darn it, I keep hitting that one. approximately 0.36. Okay. Let's get our p-value. All right, let's check the table. What are our degrees of freedom? Yeah, there are 7 counts, right? So our degrees of freedom will be 6. Really? We had a chi-squared value of 6.55. So we're going to look for 6.55 on this table. It's not there, right? So if we're going to use the table, so it's less than that. So all we can say based on the table is that our that this p-value is going to be greater than 0.25. And that's sufficient. Okay, done with B. Let's interpret this p-value. All right, so given the data that we have, this is the probability that there is no difference in the distributions of birthdays for people born before 1980 and people born for 1993. That's a good probability. So that's interpreted. Done. So what conclusion will we draw? First of all, let's go ahead and fail to reject. Yeah? Given the data, so this is, let's interpret the p-value again. Given the data that we have, there's a 0.365 probability that there is no difference, which is pretty good. That's a pretty good chance, right? So anyway, so there's a pretty good chance. So it means that, I don't know why my brain just tripped. Let's just go ahead and reject. Fail to reject. And then we conclude that there is significant evidence okay, I need to just go in the distribution in 4 people birth before 1980 and after. I don't know why I can't. Before 1980 and people born after 1980. Mm.